with just normal, simple, pure states in the Hilbert space. Then these kinds of states, if you look at the states U, if you look at some state psi, then the state U psi has exactly the same expectation values for all elements of A epsilon in an LQFT. Okay, and this is just not true in the theory of gravity. You can't find a commutant of A epsilon, as we said yesterday, and this is what leads to the statement that in a theory of gravity, if I give you these expectation values, this uniquely determines the state. Okay. So this is roughly what is meant when, not roughly, this is what is meant when we say that, in a theory of gravity, all information is available at asymptotic infinity. And this is what we proved yesterday was the precise version of that statement. Okay. Okay. So that was where we were yesterday. If there are any quick questions, I can take them now. Otherwise, I'll go on and discuss some more of the physics of these statements. Okay. So I want to discuss a little bit now the physics of the statement, and I want to give an example. We proved some statement about operator algebras, right? But one concern that people might have about operator algebras is there are many results one can prove, but what is the physics of these results, right? How does it, when you say all this information is available at infinity, or all these operators anywhere in null infinity can be approximated very well near the pass boundary, what does that mean in a physical sense? Okay? So I want to give a very simple example, and the example is as follows. Okay, so we can do this in ADS or in flat space. I'll just do it in flat space. Okay? So consider the following state. This f is a smearing function. Okay? This O is the operator I introduced yesterday. It's the same notation. This U is the retarded time on null infinity, and omega is the direction on the sphere. This lambda is a perturbative parameter that I've kept for convenience. This is not the most general state. I want to consider a state which has this perturbative parameter lambda because it makes my life simple for the simple example I'm about to give. Okay. So what is this state, right? What does this state mean? This is a unitary operator, acting on the vacuum. Okay, so there's some unitary operator that I've taken, which is determined by the smearing function f, which acts on the vacuum. And f of u omega has support only in this compact interval 0 to 1. Okay. So let me just give you a picture of what this state is. What the state is, I'll extend this picture in a while, but let me first give you a picture of what the state is. What the state is there's a shock wave, okay, that's sitting around u equal to 0. And you have acted with this unitary to kind of create this shock wave. Okay. And the shock wave has some profile, and the profile of the shock wave is determined by this function f. Okay, good. So now the question is, I was saying yesterday that all these operators on all of null infinity, can be approximated near this pass boundary, the pass boundary being here, right? And so, if that's the case, the question you could ask is, well, if I really had access to all this operator algebra, then I should be able to determine from this little region here what this function f is. So if I had some observers here, they should be able to make some measurements in this operator algebra A epsilon and determine what the profile of the shock wave is before the shock wave has reached them, right? Of course, if they're allowed to wait as an LQFT, they can, of course, determine what the profile of the shock wave is. But, if information is localized unusually in gravity, they should be able to do something here in this little region to determine how F works. Okay. So this is obviously in LQFT, observations in A epsilon do not determine F, right? And that's clear because, this whole unitary operator just commutes with everything in A epsilon. So whatever you do, it just looks exactly like the vacuum, local quantum field theory. Okay, so let's do a simple computation to show how, in fact, in gravity, you can determine what this function f is. So what I want to measure is the limit as u tends to minus . this guy is the Bondi mass. It's the integral of what I wrote yesterday, which was the Bondi mass aspect. Okay, so this guy is the Bondi mass. Notice these are different u coordinates. Okay, this u tilde coordinate I'm taking off to minus infinity. Okay, this coordinate is sitting somewhere. U is sitting in the U is sitting in the region minus infinity to minus 1 over epsilon. Okay, so U is sitting somewhere else. So this is an observation which is made really in A epsilon. Manifestly, it's an expectation value of some operator lives in A epsilon, and except it's a product of two operators, different values of retarded time, but it's some element of A epsilon that I'm measuring. Okay. Okay. Now, because I'm working in perturbation theory, I want to compute this to first order in lambda. And that's just to make my life simple. So in fact, I'll compute this and I'll set lambda equal to 0. Okay, so I just want to see what the first order term in lambda is. Okay, so let's see what the first order term in lambda is just by expanding out this state. Right? Let me remind you what the state F was. Yeah. Okay. So this is the state F, and we have to make this computation. In fact, this computation is very simple to do. Okay. Remember, this quantity of this Bondi mass as u tilde goes to minus infinity, in fact, is the Hamiltonian. Okay, it's the Hamiltonian up to some factor of 4 pi g. So this, in fact, just looks like 4 pi g times d by d lambda in the same state F of h times O of u omega prime times F. Okay. Okay. Now let's expand this out to first order and see what we get. Okay. So what you'll get will be, you'll get two terms. You'll get one term which will look like, I'll just expand this out to first order. Okay. So this looks like minus I lambda, which is some term that you get from this minus I lambda here. You get a 0, you get an O. I have too many U's, but let me go. This is a dummy variable which is sitting here. Okay. And then I have some H, and then I have this O of U. Oh, I have too many omega. Sorry, excuse me. I need a double prime here. Okay, let me put a prime here, and then I'll remove the primes here just to keep my notation simple. Okay. And then there's another term which comes the other way, right? Which is plus I lambda times 0 times h times O of u prime omega prime times integral O of u omega times f of u omega times du d omega times 0. Okay. Is this clear why you get these two terms? You know, I've done what I've done is very simple. I've just taken this state and I've expanded it out to first order. So I get one term which comes from the left, and on the right hand side you have the vacuum, right? Because the unitary, the first term is 1. And then the other side, I've expanded this unitary out on this side, and on the left side you have the vacuum. Is this clear what I'm doing? Okay.
Sorry,
okay,
I thought U was the point where you were observing, right?
Sorry, I can't hear. Please, can you speak a little louder?
Am I audible now?
Yeah, go on.
So U was the point where you were making the observations, right?
I changed the notation, so I made it U prime now. I changed this, now it became U prime because there were too many U's. So U prime is where I'm making the observation, and U is the dummy variable that's being integrated over. And there's a U prime here which shouldn't be there. Yeah. So U is the dummy variable, and U prime is where I'm making the observation.
And what about U tilde?
U tilde has gone off to minus infinity. Okay. So I replaced it with 4 pi g times h.
Okay.
Okay, good. So now you see this term, in fact, is 0 because it's the Hamiltonian acting on the vacuum. Okay, so that's just 0. So if the energy of the vacuum is 0, we just shift this insertion of h with whatever constant is required so that it annihilates the vacuum. Okay, so this is just 0. Okay, so there's only one term which remains, which is this first term here, this term here. Okay. In fact, in this term as well, you can take h through this O and move it to the left. And so really what you have is a commutator of O and h. Okay. Because once you move h through this and act it on the vacuum, you'll once again get 0. So really what you get is something which looks like, let's make sure I have my factors right. So what you get is something which just looks like minus I lambda, okay, times 0 times the commutator of OU prime, OU omega with h, integral f of u omega du omega. And then you have this place where you're making the observation. Okay. And so this whole thing just becomes this commutator. Okay. In fact, this commutator is very simple. Okay. And the reason this commutator is very simple is that this commutator, is just equal to this O of u omega times h. This is just equal to I into d by du of O of u omega. And that just comes, it comes from some commutation relations you can derive exactly in the algebra on null infinity, just by taking the symplectic form and pushing it forward. But it's kind of clear that this had to be because you see, that's what the Hamiltonian does. The Hamiltonian is generating time translations on future null infinity. Okay. So this whole thing becomes minus I lambda times 0, right, times d of OU omega d by du times f of u omega times du d omega times O of u prime omega prime times 0. Okay. Okay. Now this is something which is very simple. This 2-point function, once again, you can just compute exactly at null infinity, and that's because the algebra at null infinity is free. So there's some 2-point function in the vacuum you can just compute between do and O, and the answer that you get, I was forgetting my factors of 4 pi g, sorry. Looks like some place where I've lost my, yeah. You get some delta function that relates this omega to this omega prime in this 2-point function. So you just freeze omega prime, and this just becomes something like this. Okay. So you see, even though you're making an observation at u prime near minus infinity, and this function f has support only in 0 to 1, this 2-point function has some value still. Even though the shock wave is hitting you somewhere far in the future, you still get some value for this 2-point function. And in fact, this value looks exactly like this. Okay. Now you see, if you're given this right-hand side for some range of u prime near minus infinity, you can see that you can get f completely. And the way you can get f completely is simply by recognizing that f of u omega prime du by u minus u prime, let me replace u prime minus u up to a minus sign, okay, is just 1 by u prime f of u omega prime into 1 minus u by u prime du. Okay. And this I can just expand, and this you see looks like 1 by u prime times sum u by u prime to the power n f of u omega prime du. Okay. And there's a sum over n. Now you see, every term in this sum is different. I can identify it because I'm making observations at u prime, right? So u prime is in my hand. So I'm allowed to make observations for u prime in the range minus infinity to minus 1 over epsilon. And so I can pick out every different power in the sum by varying u prime. When I do that, you see every different power of u prime gives you a particular moment of f. It tells you what u to the n times f of u is integrated with du. So using observations for u prime in this region, we get the moments of f, right? We get all moments of f. So we can identify f to arbitrary precision.
Suvrat, you've
Yes.
assumed some 2-point function here in the algebra, right?
Yes, yes.
Like some log u minus u prime or something like that.
No. This 2-point function is exact. It just comes, it's because the algebra at future null infinity is free. So there was no, it's not like some approximation I made.
I see.
The 2-point function I used here was this u minus u prime. It comes from the fact that you understand the algebra and its matrix elements at future null infinity exactly because the theory becomes free. So there's no assumption that's going in here. I mean, the assumption is just that the asymptotic structure is what you understand.
Okay.
Which is the assumption I was making yesterday. Yeah. So you see, by making observations in this u prime, you can identify f to arbitrary precision. Okay. So this is an example of what one means when one says that all the information is available at infinity. It's a very concrete physical example. It tells you, if you had the shock wave in a local quantum field theory, you would of course not be able to determine what was happening. But in gravity, you can determine what's happening. Okay. Is this very simple calculation clear? And if there are questions, please ask me. Yesterday, I was a little worried. I was saying things which were too simple. I don't want to make the other mistake and say things which are too fast.
Can you explain what is the shock wave? Like why you are calling the state f as a shock wave?
Shock wave is just a name. It's just a unitary operator acting on zero. I'm just calling it a shock wave because it's some null excitation. So it's an excitation. You don't have to call it a shock wave. It's a shock wave is just a name. Yeah. It's not a shock wave in some precise sense, in that there's no back reaction of the metric here. So it's just some particle which have some compact support. So it's like some beam of, you can think of it as a light ray if you like.
Okay.
Or a ray of some massless particles.
So basically, given this state f, which was some integral over u between 0 to 1, I guess.
That's right. That's how the state f was defined.
That's what you're saying, that you can do some calculation in this a epsilon and you can determine this state f.
Exactly. Yeah, the calculation that we just did. It's very simple calculation, just a 2-point function.
Where did gravity enter here?
It entered in the fact that h was an element of a epsilon. Entered here.
Okay.
This was an observable in gravity, which would not have been observable in local quantum field theory. And this is a component of the metric. That's why I wrote it as a Bondi mass. So it's some component of the metric. It's the fact that there's some component of the metric that's keeping track of the total energy. But notice, measuring the total energy would not have been enough to determine f. In a classical theory, there are many different f's which would have the same total energy. Here we got much more than the total energy by keeping track of correlators of the energy with other observables.
Okay, thanks.
Okay, great.
Hi, Suvrat, can I ask perhaps a very naive question?
Sure.
So this expression where you have this sum, you said that all moments are of course accessible, all moments of f.
Yes.
If I want to reconstruct the full function, I need to really know an infinite number of moments, right?
Correct.
Does that mean that I have to make an infinite number of observations to reconstruct?
Correct. So that's what you mean. So you have to decide to what precision you want to determine f,
Yes.
and I'll come back to this later. And up to that, you have to make, so it's true, if you want to determine f exactly, you have to make an infinite number of observations. By the way, that's always kind of true. If you want to determine f exactly, you have to determine anything exactly, you have to make an infinite number of observations.
I mean, in a series expression like this, I would have to do that. That is true. So I was just wondering whether, so if I want to really completely, exactly capture f, and if the statement is that I have to make an infinite number of observations to do so, correct. Is it fair to say that I have all the information available?
Well, it's always, you see, I'm not, so I want to make a slightly different point a little later, but you see, the fact that to exactly capture some function, you need to make an infinite number of observations is just always true, right? Because otherwise, how do you know? Let's say you could directly measure f. Right? Let's say you measured it at 10 different points. You don't know what it's doing in the middle.
So can I put it in a slightly different way?
Yes.
So for example, let's say every observation that an observer makes needs some amount of energy. And if you specify to me that, okay, I want to capture f up to this precision, of course, there's a 1 over that cutoff, which will set me the energy. So the point is that I have an energy budget also. Doesn't that couldn't the case be made that if I want to make more and more precise estimates of this, I would need more and more energy, and therefore I might start back reacting on the geometry.
I want to say a little bit about what you're saying, but I just want to say the way you phrased it right now, there
Yes.
isn't really a difference between this observer at infinity and the observer who sits here and tries to make a measurement, because the observer who sits here also has to make measurements. Let's say the observer just has some detector which measures U, right?
Sure,
But
sure,
really, they can only measure F at some discrete time intervals depending on how accurate their detector is.
sure.
So even they need infinite amount of energy in order to measure F exactly, because maybe they measure F at 1 femtosecond, but they don't know what it's doing in the middle, right? So this is just always true. Now, maybe what is slightly different, and I'll come back to this, is that the observer at minus infinity has to work in terms of the moments of F.
Yes.
Right? Whereas the observer here can work in terms of, maybe F directly. Okay?
Mhm.
So it's true that for both of them, they need some infinite amount of energy, but it's true that the observer at A epsilon is working in a slightly unnatural basis, in that there might be two functions F, which you could determine are different, but from the moments are hard to determine are different. And I'll come back to that point.
Yeah, okay. Maybe I should.
I'll come back to that point. It's true that, it's of course more natural to just directly measure F, right? The information is much easier to access if you have a detector who's just measuring something here.
Yes.
But the fact that, to get infinite precision, you need infinite observations, infinite energy is always true. That's
Yeah. So I guess my sort of, I was trying to understand the statement that whether, I mean, it's this fact that, I mean, to what extent it is reasonable to expect that I can safely ignore back reaction and still talk about.
Yeah, we'll come back to that. Back reaction, not a problem, because you're working at asymptotic infinity. That's the way all this is phrased at infinity. That's the reason I wanted to say phrase everything at infinity, as opposed to being in the bulk. At infinity, you can do whatever you like. You can imagine that you have flat space, and so at infinity that things are really free. So that's why you don't worry about back reaction for observations at infinity. I think what you're saying would be relevant if you thought of observation somewhere in the bulk.
Okay, yeah, so please continue.
But I'll come back to some of these points. Yeah. Okay.
Okay.
Let me say something about causality. Okay. So one thing people say is, well, how is this consistent with causality? Right? This shockwave happened here. There's some bomb which went off here, and there's some ray of light. And how are these people able to determine what's happening here? Of course, the point is that there's no violation of causality. And that's because when I made this diagram, I was being a little deceptive, right? Let me copy this diagram and tell you why I was cheating a little bit. I wasn't cheating. I just didn't draw the full diagram, right? You see, in a theory of gravity, there's no such thing as a bomb that goes off in the middle of space. You can't just inject energy somewhere in the middle of space. So really, you should think of the full state. And the full state also has past null infinity. And this thing came from something at past null infinity, right? So there was no violation of causality. So what is really happening here is that in gravity, we cannot inject an excitation. Maybe if you start doing very complicated things, the observers near this past boundary of null infinity can do things that look very complicated. But this is something very simple, right? Just a 2-point function. So there's nothing fancy, no violation of locality or anything of causality that's happening here. And what we are seeing here is we cannot insert an excitation from I minus and erase its traces. Near I plus minus. I plus minus means this, the past boundary of future null infinity. Okay. So when you inject an excitation from infinity, you can't erase its traces. By the way, we're already familiar with something of this kind, which is just the total energy. You see, we could ask, how do we know the energy of the sun? We are sitting here, the sun is there. What if the energy of the sun suddenly changed? How, But the fact is, it can't happen, right? We know in a theory of gravity, the energy of the sun can't suddenly change from what it is to half of what it is. That can't happen without some radiation crossing us in some way. And so the way we know the energy of the sun is that, some matter went and formed the sun. And when that matter went and formed the sun, it crossed the point where we are at. Here, I'm assuming that, only the earth and the sun exist in the universe. And when it crossed the sun, it modified the metric in such a way that, the Gauss law still keeps track. The metric still keeps track of how much energy went in. And so this is an important physical point. It's not like something is jumping from one point to the other point. It's rather that the information never goes in. It's not that it jumps from inside to outside. And, so this is one thing which a physical simple point which one should keep. Okay. Let me just say this in another way, what I just said. You see, in LQFT, we can prepare split states. Split states are states where you have some excitation A here, and it looks like something else here, A tilde. So this is by A, I just mean, let me use something else, some other symbol. I just mean maybe it looks like the vacuum here, and excitation 1. And you can think of another state where it still looks like the vacuum outside, and it looks like a different excitation inside. Right? And so what we have done when we create such states is that we have kind of put the energy or put the excitation, we have localized it all inside this bounded region, while keeping things looking like the vacuum outside. And what is different about gravity is one can't do that. That's what this simple calculation kind of is teaching us. Okay. So now I want to spend just I'll come back to the question that Arnab asked about, how do you get back locality? How do you get back approximate locality and so on? But I just want to spend 5 or 10 minutes trying to explain physically why it is that, such split states are hard to make in a theory of gravity, why the information is available at infinity. Okay. Are there any questions about the statement? Once again, before I'm now going to say something which is a slight, very non-algebraic, just physical statements. Okay.
No questions in the chat, Suvrat.
No questions, right? Okay, fine. Okay, great. Okay, great. So you see, let's just go back to something very basic, right? The basic thing is the uncertainty principle. How do we really localize excitations in quantum mechanics? Right? So if you give me an excitation which is just delocalized in position space, such an excitation can be very sharply peaked in energy space. In fact, the uncertainty principle is generally about position and momentum, but energy goes together with momentum. So if you want something that's really sharply localized in energy, you see you can't completely localize it in position space. Okay? Now, usually, what do we do? This doesn't prevent us in quantum mechanics from creating some superposition, some excitation which is strictly localized in some region, right? As I said, we had these split states, which you write down in local quantum field theory, which are really have some excitation in some region and have nothing outside. And the way they work is like this, right? You take these energy eigenstates, and this is some degeneracy, different energy eigenstates might have degeneracies, and you sum them. Okay. And if you do this, you can get something that's strictly localized in position space. And it's not localized anymore in energy space because, I've summed over some large range of energy eigenstates. In fact, you can check to get something that's strictly localized in position space, I really need to sum over an infinite number of energy eigenstates. Okay. So this is just something very basic. It's, how do you create localized excitations in quantum field theory? Well, you create them by summing over lots of energy eigenstates. Okay. Same way you create localized operators. Since we're discussing algebras, if you want to create localized operators, the way you create localized operators is you take operators, you can associate energies with, you can think of operators which also have a well-defined energy, and you superpose a lot of them so that you get something which is localized in position space. That's what a local operator does. A local operator has an infinite number of operators that have well-defined energy. Okay, why doesn't this work in a theory of gravity? In a theory of gravity, you really need to satisfy the Wheeler-DeWitt equation, right? You need to satisfy. It is called the Wheeler-DeWitt equation, but really, the part of the Wheeler-DeWitt equation that's important for us is just the Gauss law. And the Gauss law tells you that states are of the form you have some energy eigenstate maybe in the matter sector, and then you have some term at infinity that keeps track not of the which energy eigenstate you're in, but of what the total energy is. Okay. Here I'm thinking in some very semi-classical pictures. So I'm just trying to give you some physical intuition for how this happened. Okay. So these are states which satisfy the Wheeler-DeWitt equation schematically. Okay. In that, if you thought of some big Hilbert space where you had some metric degrees of freedom and some matter degrees of freedom, and there was some direct product Hilbert space, not all states, you can't just take some arbitrary direct product of what the matter is doing and what the metric is doing. Rather, you have to take some particular combination. And the particular combination is you have some energy in the matter sector. This matter could even be transverse traceless gravitons. And then, there's some degree of freedom at infinity that keeps track of what the total energy is. Okay. So this is one constraint you have to satisfy in order to satisfy the Wheeler-DeWitt equation. You have to do more, but just to satisfy the Gauss law, the states have to be of this form. Right? Now, let's say you try to play the same trick that you played previously, where you took a superposition of energy eigenstates, right? So you now try to do well, but now you have this guy sitting at infinity, and this guy sitting at infinity prevents you from arranging for your states to have destructive interference outside some bounded region and have constructive interference inside that bounded region. Okay, so the tails prevent destructive interference outside a bounded region, but constructive interference inside. Okay. You see, let's say you say that, well, I want to fix the energy. Let me just fix the energy to something which is some total energy, right? If you fix the energy to some total energy, and then you said, I want to get rid of this part. So you could do that, but then you would find that you were summing over degeneracies of different energy eigenstates, not summing over n anymore. That's the difference between what I wrote previously and right now. But you can check, and this is a simple check. If you just are allowed to superpose states of a given fixed energy, then using that, you cannot generate a strictly local excitation. If you look at states of a given fixed energy, those states are all localized out, are all delocalized. And there are always some other observables at infinity, not the energy, but some other observables at infinity that can distinguish these different states for you. So these states at fixed energy do not correspond to strictly localized excitations. Okay. So what I said right now in the past 5 minutes is just a physical, it's just some physical and slightly hand-waving explanation for what we proved yesterday in terms of algebras. Okay. So let me just recap. Okay. So what I've said so far is that, algebras in gravity have this unusual property in that, the algebra out at asymptotic infinity, even in a small part of a small time band of asymptotic infinity, knows about the full algebra. This tells you that, information is available out at infinity. It's something pretty physical in that, you take some simple states, you can check already, even in simple perturbation theory, that information is available at infinity. And physically, the way to understand this is that when you think of states which satisfy the Wheeler-DeWitt equation, these states, have to have these tails at infinity which keep track of the total energy. And these tails make it hard for you to arrange for destructive interference outside a bounded region and constructive interference inside. In fact, one way to reprove the result we proved about algebras yesterday would be to try and show that if you had, in any theory, if you fix the total energy so that the tails then don't matter, then, within the set of states of an exactly same energy, you can't generate for localized excitations. And that's kind of physically clear. It comes from the uncertainty principle, although the argument we gave yesterday can be thought of as a more formal statement of that. Okay, is this physical intuition kind of clear? And just to say once again, the whole issue here is not an issue of information jumping from one place to another place in some way that's faster than the speed of light. It's a question of how the constraints force states to behave. And constraints don't allow certain kinds of states in gravity, and they do allow certain kinds of states in the absence of gravity. Okay, okay, is this clear? Are there any questions about this?
No questions in the chat, Suvrat.
Okay, fine. So, okay. So then I'll go on, and I want to go back to some of the questions that were asked yesterday also.
Sorry, Suvrat, can I ask you a question?
Sure, yes.
Yeah. So, Gauss law constraints exist also in other gauge series, like in QED. So, but somehow this particular, the last thing that you said about, the wave functions being constrained. Yeah. They don't matter there?
Exactly, because you see yesterday, remember in the proof that we did yesterday, what was crucial, I'll go back to the formal proof. I can give you several answers to that. You see, what was crucial in the proof yesterday was that we had this projector on the vacuum, right? Yeah. You could, in fact, there's a projector on a cyclic and separating state, okay, which you can write down, which lives in this algebra at infinity. if you think of the projector onto states of zero charge, it doesn't project you onto one state. It projects you onto an infinite manifold of states. So, by measuring the total, this is very important. The fact that, in gravity, you have this projector on the vacuum, which is an element of the algebra. It projects you onto a unique state, or, some set of states which might be labeled by super translations, which the projector on the total charge doesn't. Let me give you another physical answer based on just what I said right now. You see, there is no uncertainty principle that goes together with charge. There's nothing that tells you that an excitation of a fixed charge has to be delocalized. Whereas there is something that tells you that, if you have an excitation of a given energy, of an exactly fixed energy, that is not a localized excitation. And another way to understand the same thing is that, if you fix charge, you can always have positive and negative charges. Right? So you can always combine positive and negative charges, create something of zero total charge, which is just completely localized. So you take a Wilson loop, just a Wilson loop, and this is a completely local gauge invariant operator, creates a local excitation in some region which has zero total charge outside. And there is no such analog in gravity. There are no such local gauge invariant operators. Does that answer the question? Or?
Yes, yes. Thank you.
Okay. Are there any other questions, sir?
Suvrat, can I again ask a very brief question?
Huh.
So just to, I understand the statement that not every state will satisfy the Wheeler-DeWitt equation. That's fine. So now, if I go back to your earlier picture where you have basically the geometry, which is, and then there's an observer who's making observations at A epsilon, for example, A sub epsilon. So if I think about the combined state in a semi-classical sense, so that state would satisfy the Wheeler-DeWitt equation?
Yes, it would. It's important. It's this kind of a state. So you can explicitly write down these solutions. So that it's a state where the matter is in some state, but also there's a metric component which is entangled with that state. So the Wheeler-DeWitt equation picks out particular entangled combinations of the metric and the matter. So the matter is in some energy eigenstate. And so, this thing which was a shock wave, which was really a superposition of different energies, which made it interfere destructively. In a theory of gravity, the different energies, it's not just the same superposition. You have to take the different energies, you have to dress them with the metric, and then you superpose them. So it's some combination of this kind, this shock wave. And because it's a combination of this kind, that's why you can extract these coefficients Hn by making some observations at infinity, which allow you to extract this part. And then after that, you make some additional things that let you get An. So that's what we did in this language.
I see.
So
And
when
sorry, you were about to say something.
No. So I was just saying, if you think in terms of the structure of the constraints, it tells you can't just be, you shouldn't first superpose and then satisfy the constraints, right? You have to satisfy the constraints and then superpose.
Yes.
And so that's why the information becomes available outside. So
okay. And if I imagine taking this observer slightly inwards, and then would that state start violating the Wheeler-DeWitt equation?
Well, the state always satisfies the Wheeler-DeWitt equation. Then you would start asking, what are the observations that this observer who's gone slightly in makes? Then this observer is not measuring H boundary, but is measuring something else, which is not quite the boundary energy, but something inside. Physically, that observer can probably also determine what's happening. The reason this is also the discussion we were having yesterday. You just have to be much more careful about how to define this observer, what this observer is measuring, back reaction, all the other issues that we were discussing. You have to be more careful about once the observer goes into the bulk. I don't think physically there's a problem, but just to make everything precise, I think is tricky. And since we are saying these are counterintuitive properties anyway, one needs to be very careful. So this is, I guess, also what I was saying yesterday. It's not that there's a fundamental obstruction to going into the bulk or a fundamental reason to work at infinity. It's just that infinity is where you can make the most precise statements without having to worry about many other potential complications that might appear in the bulk.
Okay, thanks.
Hi, Suvrat. Kind of follow up to Gautam's question. Are you making these statements on gravity for the full quantum gravity? Because you mentioned about these Wilson loops for QEDs. So for a given semi-classical theory of gravity, I can still make some analog of these gauge invariant observables in the gravitational.
Not locally, right?
No, not locally.
So there are, so that's the.
No, I mean, Wilson
there
loops are also not.
No, Wilson loops are local. They're localized in a region. I mean, by locally, I don't mean you have to localize them to a point. They're inside a region. So in gravity, there are no such observables which are gauge invariant, which are localized to a region inside. So the statement we proved yesterday was some statement about algebras, which really was a statement in some full theory, because that's why I said we work at infinity, because you think the algebra should make sense also in the full theory. Today, what I'm saying is just something which is, as you say in the semi-classical picture, just to say that what we are saying yesterday is not a very formal statement, it's some physical statement. Okay. So now let me emphasize something else. Let me go back to this question that Arnab asked, and also some questions that were asked yesterday. Okay. Which is, you see, it's true that you can get energy at infinity, right? Or you can get information at infinity by doing these kinds of tricks. But in fact, it's not always, what this procedure that I outlined works in terms of moments of this function f, right? And you could have two different functions f. We had some answer here. You could have two different functions f, which had, where the moments were it was very hard to distinguish them in terms of the moments. But, in terms of looking at the function f, one of them has a small bump in one place, the other has a bump in a different place. These bumps are kind of arranged so that all the moments up to very high moments are the same. So for a state of this kind, or for a shock wave of this kind, some observer who was directly making observations at that point it would be much easier for that observer to determine the difference between these two states than some observer who lives out at infinity. So it's certainly true that, there's a price you pay by trying to get information from infinity. And this leads us to some notion of approximate locality, which is an important notion. And I want to also explain some of this recent paper, by Bahiru, Berlin, Kyriakos, and so you see what, and this is an important point. So, there's a certain price, as I said, you pay to getting information at infinity. And therefore, if you make the right kinds of approximation, so you restrict the powers of the observer at infinity in the right way, then it is possible to get approximately local operators in the bulk. Okay? And I want to explain how that happens. So we need to do two things, right? First, we need to restrict the ability of the observers at infinity. Okay. So in particular, here's one way in which we could restrict the ability. Let's go back to ADS. I'm kind of flipping seamlessly between ADS and flat space. In ADS, it's convenient because you have a natural notion of complexity, and it comes by looking at this number n, which is the ratio of the ADS scale to the Planck scale. Okay? And then we could consider, and you can do something, of course, very similar in flat space, except you'll have to invent some other parameter which will determine complexity for you, which is why I'm going back to ADS. Okay? So let's now look at a coarse-grained algebra, which is the same algebra that we discussed yesterday. It's these products. Up to n, like products up to n. Okay. But I restrict this n to be much smaller than n. Okay. So this is now a coarse-grained algebra for these observers at infinity. So these observers can't measure everything. You can include the Hamiltonian in this algebra, but they can't measure all correlators. They can only measure low-point correlators. Okay. The second thing you need to do is consider a heavy state. Not empty ADS or not flat space. And by heavy state, it means that you draw psi from energy E, where the density of states scales like some power of n. Doesn't have to be n exactly, it could be n to the power half, but scales like some power of n. Okay. Now, if you, so now I want to say, if you do both of these things, first, if you restrict the algebra, the elements of the, the abilities of the observers at infinity, and you consider states which are heavy states, okay, if you do both of these things, then in fact, you can define some approximately local operators. And I want to explain how that happens. So for a typical state, we would have a psi is not equal to 0, okay, for all a belonging to this a epsilon force. Okay. Why is this the case? Well, it's very simple. The number of states that you have, the size of A, is not very large. The size of A is something that doesn't scale with n. Well, the number of states you have, does scale with n. So, it can't be, for some typical linear combination that you take, you will in general not be able to annihilate the state by acting with an element of this algebra. Okay. So this state is what's called separating with respect to this coarse-grained algebra in algebraic terms. So it's a separating state. In this paper, it's important that it's a separating state. They phrase this in terms of the fact that the h minus the identity on the state is not equal to 0. So this is true even when you include the Hamiltonian, right? If you draw things from a thick enough energy band, then even acting with the Hamiltonian or h square and the Hamiltonian is not enough to annihilate the state. Okay. And as I said, this just follows from counting the dimension of the algebra and counting the dimension of the relevant Hilbert space. Now, we can find an operator Q, which has the property that Q psi looks like the action of some local operator on the state psi. Okay. And also Q A psi is equal to A phi free X psi. So this operator Q, when it acts in the state psi, it looks like, some simple local operator, which you would have defined in the free theory acting on psi. But if you act it on A psi, then it commutes through and it acts this way. How do you know such an operator A exists? Well, just take the RHS to be a set of linear equations. Take the above to be a set of linear equations. How many equations do you have? Well, we have as many equations. We have dim of A epsilon course plus 1 equations. Plus 1 comes from here. Okay. And, all these equations are consistent. And the reason they're consistent is that A psi is never equal to 0. If A psi had been 0, then, we would have been in trouble because we would have been writing Q on 0 might be equal to something that's not 0. Okay. But because A can never annihilate the state, so these equations are consistent. And you see, it's natural that they're consistent. That's because this operator Q acts in a big Hilbert space. It's a Hilbert space that's much bigger than the dimension of this coarse-grained algebra. And therefore, we have now found an operator phi, Q that acts like some free field operator, but that also commutes with this coarse-grained algebra. Okay. So this is the sense in which you can define approximately local operators even in gravity, provided you do two things. You coarse grain the algebras, and provided you think of heavy enough background states. Okay, is this construction clear? What I said right now? If there are any questions about this, because there were some questions yesterday about this, so this is the right time to ask them if there are questions about this how you recover approximate locality in gravity.
Oh, sorry, maybe a very naive question, but so the statement of approximate locality is within the bulk, and
Yes.
The coarse graining is for the observable algebra at the infinity, like the
Correct. So what I'm looking for are some observables in the bulk that commute with things at infinity. So what I want to say is, if I coarse grain the observer, if I coarse grain the abilities of the observers at infinity, then they cannot determine what's happening in the bulk exactly. So it's in that sense that I'm trying to hide information from what's happening at infinity.
Okay.
And so it's true. What you say is true. That's because if you take the algebra at infinity to be infinitely fine-grained, it becomes the whole algebra. And so that's why you have to coarse grain the algebra at infinity, and then you can find a commutant for that algebra. So what I'm trying to do precisely is find a commutant for the algebra at infinity.
Thanks. Yeah.
Okay. Let me
I see that I have one question. So is it true that the Hamiltonian is also part of A course?
Yes, Hamiltonian is part of A course.
I see. Okay, thanks.
You see, it's part of A course, and it's important that when the Hamiltonian is part of A course, that's why you can't take a state which has a very small band of energies. You see, if you look at this paper, this condition here. So for instance, if it was true that H minus some E naught times psi should also not be 0 or should not be close to 0. So H can be part of your coarse-grained algebra, but your state should have enough spread in energy that by acting with H, you can't annihilate it. It's important once again that, it's only H and some powers of H. If you include arbitrary powers of H, then this won't work. So it's important that you have to coarse-grain here. Otherwise, the whole thing will not work.
No, but this psi could be an eigenstate of H, right?
No. If it's an eigenstate, then it will be 0. So that's why it's important that you take a typical state, and that's why it's important in this whole construction that it shouldn't be an eigenstate.
I see. Okay.
Okay.
But sorry, I'm still like to push just one last thing. So this is some state in some thin energy band around E naught.
Yeah, with some finite energy, but that's right. Or large energy band, yeah.
Right. So, but it's a linear combination of all those states. So H minus E naught applying on psi would still be close to 0, not perhaps exactly 0.
Sorry, I'm not.
That's acceptable.
Sorry.
Oh, okay. Yeah. Okay. We can talk about it later. It's okay. My audio perhaps is not great. We can talk about it.
Yeah. Sorry. I don't know if could someone understand what you said? What Dunya just asked. Sorry.
Yeah. I don't know if I'm better audible now, but I'm saying we can talk about it later.
Okay, fine.
My audio is
about it later. Okay, fine. Okay, great. So let me say a few things. Okay, let's say we look at special classes of states. Look at a set of atypical states. Atypical state psi. So let's call them psi I, right? Where I goes from whatever 1 to something. But not all states of a given energy. But let's say we look at a set of atypical states. So I goes to 1 to some cutoff. Okay, let's call it lambda. Then we can find Q that works correctly in all such states. In all such states. Okay. In fact, this is related to older constructions of DeWitt and others. Let me just explain this a little more. Let's say you want to think of states where, you're not an empty ADS, but rather you have some supernova or some big classical background, okay, some classical star. Then one way to localize, this was also related to a question that was asked yesterday. One way to localize an operator in the bulk would be to say, well, you take the field phi and you act on it when the matter density becomes some value. This kind of operator is an operator which is dressed to the classical backgrounds of the star. Okay, it's not dressed to infinity. And so this kind of operator commutes with your coarse-grained algebra to a high approximation. In this construction that I just demonstrated, the way you would construct, this was the older construction of DeWitt. Okay, this is how DeWitt thought of these algebras. In that, you write down phi, some field phi, but it acts when the matter density takes on some value. So you take phi of x, you integrate it with delta of the matter density minus some value, integrate over all x. So phi acts not at some point x, which is specified from infinity, but rather at some point where the matter density takes on some value. Now, this kind of operator commutes with the boundary algebra to good approximation. Of course, not exactly. We proved yesterday there's nothing that can commute exactly. And in the construction I just presented, the way we would construct this operator would be by recognizing that the star is an atypical state. It's not a state in equilibrium. It's a state which is out of equilibrium, and that's pretty important. And it's an atypical state, and you take this atypical state and you construct this operator Q for all these atypical states. So you construct Q1, so for each psi I, construct Qi that acts correctly in the vicinity of psi, in this code subspace about psi. And then you write down some big operator Q, which is just the sum of all of these Qis. And this operator Q acts correctly in all of these atypical states and in the vicinity of all of these atypical states. Okay. So if you think of these older constructions of Divot and so on, which worked about atypical states, then you could use the construction I just presented and, sum it over all of these atypical states, and you would get some state independent operator which would work in all of these atypical states and which would approximately commute with the boundary algebra. On the other hand, if one considers typical states, like typical black holes, then there is no state independent Q that commutes with A epsilon even after coarse graining. Okay. In all states. So in particular, if you ask for a unitary operator U, and when you say an operator is unitary, it's important that you have to specify what it means, how the operator acts on all states. There's no point in saying an operator is unitary on one state. Then there might sometimes be no unitary operators that can commute with the boundary algebra, even if you coarse grain the algebra, if you look at typical states like black holes that do not have features. Okay? So what's special about a typical state is a typical state like a black hole doesn't have some feature like a star that you can dress things to. Okay? So this kind of construction that I just presented, it works well when you look at atypical states which have features which are out of equilibrium, and if you look at typical states, then you can still find some state dependent operators, but you can't find state independent operators, and you can't find unitary operators in the bulk that commute with A epsilon, even if you coarse grain A epsilon. Okay. Now, this may or may not be a problem depending on your perspective, but what I said right now is some statement. It's a mathematically correct statement, and then we can discuss what its significance is.
Excuse me, I had a couple of questions.
Yeah.
So whenever you are mentioning boundary algebra, you mention A epsilon, right?
Yes.
And the second question is, could you clarify why a black hole is a typical state and the classical star is an atypical state?
Why is a black hole a black hole is a typical state is just, so I was thinking here of large black holes in ADS. Maybe I should be clear, like a typical large black hole in ADS. So you're right. I should be a little bit more precise. If you think of black holes in flat space or small black holes in ADS, they're not typical states. Yeah. But large black holes in ADS, they dominate the ensemble because the entropy is the full entropy of the boundary. So there's nothing else. That's why they're typical states. Whereas stars in general do not dominate. Stars don't dominate the ensemble. So if you look at a typical state of energy n squared in ADS, it's not a star, it's a black hole. There are, of course, other states which have the same energy, but they're atypical.
So a rough idea would be like large entropies, states having large entropy would be a good example of a typical state.
No, states which are, states which have large entropy and are in equilibrium are good examples of typical states. Right?
Okay.
States, to get these kinds of approximately local operators in a state independent way, at least, you can decide whether or not you want that. You need some features which are out of equilibrium. So you need some star, something which is different at one point and different at some other point. And also, in order to fix the time of the operator, you need some time dependence in the geometry. So typical states don't have such macroscopic time dependence.
And by equilibrium here, you mean thermal equilibrium?
Yes, exactly. That's right.
Okay, thanks.
Okay, can I also think of it in terms of like having some quantum hair or something being typically?
It's not quantum hair, it's classical hair actually. What you need really is classical hair in order to find these approximately local observables. So you need some classical background in order to find these approximately local observables.
Okay, thank you.
Okay, this is, so in particular, one point I want to make since this question, observers provide an example of such, classical backgrounds. So there's all this recent work. I think this was asked yesterday. In fact, there's this work by Christian Jensen and Sorce and Speranza, and also this work by Witten, Chandrasekhar, Pennington, Chandrasekharan, and Longo. And in all of these cases, they're trying to define algebras. So in this paper by Jensen, Speranza, and others, they're trying to define some entropy of some bulk regions. And the way they do this is by introducing an observer. So the observer is very important for this. And the observer allows you to define an approximate algebra in the bulk that commutes with something near the boundary. Okay? So the way you should think of the observer is as a state observer has energy which is much less than n, so it doesn't back react, but it has energy much larger than 1. In fact, the key point here is it has, energy, it has density of states is much larger than 1. So in the presence of such a background observer, you can define these approximately local observables. Okay. In fact, since this is a workshop and hopefully there's some students who are still following this, and I have not lost them. An interesting point is to try and make this precise. Okay, so in these recent papers, the way things work is, they introduce these observers and then they try to, they try to not impose the full Wheeler-DeWitt equation, but rather impose some restricted set of constraints. In fact, it would be nice to make this precise. Okay.
So, Brad, before you proceed, there's a question in the chat related to your previous point. So let me ask this. So is it that a state corresponding to a saddle in entropy calculation could be associated to a typical state?
No. So I wasn't thinking of an entropy calculation or Euclidean path integral in any sense. There's no, everything here is Lorentzian. So typical state really meant, you take some set of states at some energy and take some state which is hard typical. So for a black hole, we know the entropy. So the saddle in entropy calculation usually is some Euclidean geometry where you compute something. Okay, but here I wasn't thinking of doing any Gibbons-Hawking path integral. I don't know if that was the question, but yeah. Okay.
Yeah.
So it would be nice to make what I just said right now precise. In that, it would be nice to model the observer as an excitation in the global Hilbert space. And also see how the size of the observer, by size I mean the conditions above, can impact the coarse graining of A epsilon. Okay. And in these papers, this has not been done. Rather, we have an idealized observer, and the idealized observer can make measurements of time which are arbitrarily precise. And this is not exactly correct. It's some idealization. And so, in fact, it would be nice to just model the observer as a heavy background, and then see, how when you coarse-grain the boundary algebra, you can write down some excitations that approximately commute with the coarse-grained boundary algebra. How well they commute will depend on the size of the observer, and all of these things can be done. So this would really be, the framework in which all of this could be made precise, but this hasn't been done.
But in the context of ADS-CFT, isn't this the work of Lampros and Jeffries?
Lampros and Jeffries. No, they're trying to do something different. They're trying to use an observer, some black hole as a probe.
Yeah. Okay.
So they're not trying to do this. This is these more recent papers of trying to define these local algebras.
I see.
Okay, good. So now I want to say one more thing. And then maybe in fact, since I have a little bit of time, I can say a little bit about how things work in Disita. But let me just say one more thing. So far, just to recap what I've said, right? I said at the beginning, yesterday we had some formal result about algebras. Then today we said, well, it's not just a formal result. Well, there are also some low energy checks you can make of this. We had some physical understanding of how those low energy checks work, why it is information is localized unusually in gravity. And then, we said, well, okay, But if you coarse grain the boundary algebra and you think of a heavy background state, especially nice is a state which is atypical, where there's some dynamics in the background, then by doing this, you can write down some approximate local operators in the bulk. We explained how to do that. Okay. Okay, good. But there are some cases where this is still important, right? The fact that information is available at infinity is still important for some questions. It's still important for some questions, even for heavy states. Okay. What is an example of such a question? Well, an obvious example of such a question is a question of the unitarity of black hole evaporation, right? You have a black hole, maybe it's a small black hole in ADS, it evaporates. Then you want to ask, well, is it pure or not, right? For such a question, you cannot ask a coarse-grained question. Right? It makes no sense to ask questions about the purity of black hole evaporation. We must ask a fine-grained question, okay? That's because if you coarse grain the algebra and you say, well, my observer at infinity can only measure like some operators up to some n, then anyway you're not going to see the purity of black hole evaporation, right? So to see the purity of black hole evaporation, you must ask a fine-grained question, right? And up to an accuracy of e to the minus s of the Bekenstein-Hawking entropy. And otherwise, it doesn't make any sense to ask these questions. So if you ask fine-grained questions, then the result we proved yesterday, which was some precise algebraic result, tells you that it's still true that the information is available at infinity. Okay? So just to say, one shouldn't tip the balance too far on either side. It's true that information is available at infinity. This is important about simple states. It's also true that in a heavy classical world, there are approximate local observables. You can't just get everything out at infinity. But on the other hand, the fact that information is available at infinity is important conceptually, even about heavy states. And the reason it's important is if you want to ask fine-grained questions like, is black hole evaporation, does it preserve information? Then, you better keep track of all of these fine-grained degrees of freedom. Okay? Otherwise, you shouldn't then ask about coarse-grained algebras. You shouldn't be talking about coarse-grained algebras because, that's not consistent. Okay. Let me say now just one more physical thing. Okay, how should you think about, since I said something about black hole evaporation? Now, how should you think about why black hole evaporation is a unitary process from this perspective? Okay, so I want to say something which is slightly imprecise argument. I'll say why it's slightly imprecise. Okay, slightly imprecise argument for why information is preserved. Okay. You see, one argument for why information is lost is the following. We think of the black hole, we think of the horizon, and we say, this was Hawking's argument actually, which is the horizon is featureless. It's featureless up to some constraints imposed by the no-hair theorem, right? So you have the no-hair theorem. It tells you can measure some total energy, but you can't measure anything else. Right? However, what we've been saying so far tells us that the horizon is not featureless. Okay? So the discussion that we've been having about how information is localized tells us that if we keep track of the constraints carefully, not the way one would do in a classical theory, the horizon is not featureless. So it's not true that there's some no-hair theorem in the full quantum theory that tells you that the region outside is just determined by some macroscopic parameters. That's a classical result. And it's clearly not true in the quantum theory. The reason this is a slightly imprecise argument is because I'm making reference to some region in the bulk. I'm trying to say something about what's happening at the horizon. And, that's not, as we've already had several discussions about, that's something which is hard to make precise. Okay. However, one way to think about, how the information is preserved is that when the information that went in to make the black hole, this was the infalling matter in the past, it left an imprint somewhere here at the horizon. Okay? Just like, by the way, it left an imprint for the total energy. You know what the total energy of how much total mass fell in. Okay? So this leaves an imprint at the horizon or outside. It leaves an imprint outside in terms of correlation functions of the metric and other fields. As I said, I want to emphasize, I'm not making a very precise statement, but this is a physical way to think of how the information is preserved. It's the fact that when you throw in information from outside, that information leaves an imprint outside. So sometimes there's some criticism of some of these ideas, which says that, well, the information was inside the black hole. How did it jump outside? Well, it never jumped outside, as we discussed several times. The information never really went inside. There was some imprint that is left outside. And so that imprint also affects the formation of Hawking radiation. This is a slightly different picture from the kind of picture that's sometimes proposed in the fuzzball. Okay, so the fuzzball says something similar. There's some horizon which keeps track of information. And that's because in the fuzzball, we're not trying to say there's some classical feature of the geometry that's keeping track of the information. Rather, we're saying, look, there's some wave function. That wave function you look at looks, in the classical picture exactly like a black hole. But if you keep track of these complicated correlation functions, then, they have some information about what went inside. And it's not something that requires us to make strong assumptions, or that requires us to find classical solutions. It's something that follows naturally from the way quantum gravity works. Okay, let me conclude my last 5 minutes and say something about islands, and maybe since I have 5 minutes left, and how islands fit in. Okay, so there's also, I think,
sorry, I think I misunderstood something.
Yes.
When you say leaves an imprint outside, do you mean it in a classical sense or in the full quantum
No,
sense?
in a quantum sense, in the sense that, if you look at correlation, you see in the classical sense, there's nothing more than the total energy. Hawking was right in that, so everything, no, clearly not in the classical sense. It's the same. I want to extend this picture to a black hole. Look here. You see, in this picture, I injected some energy from infinity, but these observers, by measuring a 2-point function of HO, which was very much a quantum mechanical thing they were measuring, right? They were measuring this guy. They were able to determine what had gone in. It's really, I'm saying, well, physically, you should think of the same story for a black hole, except it's not a 2-point function, but you need to measure an S-point function to very high accuracy to determine what went inside. Okay? But the same way that, when in this picture, something went in from here, but these observers, by making some measurements here, could determine what was happening. And the reason they could determine it is because this thing that went in left an imprint outside. It's not that the information jumped. So I want to say, physically, you should think of the black hole from the same way, that, there's some information which lives in quantum correlations. Classically, even in this simple example, there's no information outside. See? And that's what leads to unitarity of the evaporation. Again, I want to emphasize this is a physical argument. It's not the precise argument is the algebraic result we were discussing yesterday.
Also, just to clarify, is it the same idea of the black hole complementarity?
Well, black hole complementarity there are various things that were said about black hole complementarity, and people use it in different ways. One picture that was used was
the idea of Uglum and Susskind.
Yeah. So okay. So one. Let me just say, it's indeed sometimes this is said to be a version of complementarity, but I want to emphasize the following. What I'm saying right now is not some assumption that there are two different descriptions for an observer outside, for an observer inside. Right? What I'm saying right now is, if you look at the constraints of gravity, they force the structure of the states to be such that at infinity, information about what's inside is already present. So it's a more precise result in that sense than a postulate that there's some description, one description for an observer outside and one description for an observer inside. Rather, it's a statement that the constraints tell you that these arguments of the classical no-hair theorem and so on are incorrect. So it starts from a more conservative set of assumptions, and you don't need to postulate something.
And this is true when you analyze the full set of Wheeler-DeWitt constraints.
That's
not
correct.
Restrict. Okay.
That's correct.
Yeah.
It's true that similar ideas were said in the ways of complementarity, but and in fact we also use this phrase a lot in our earlier papers. But I think I've learned a little bit that complementarity is thought of in very different ways by different people. So I hesitate to use the phrase now. What I'm saying right now is a little more precise. Okay, good. Let me just say one thing about islands, and then in fact I can stop. So you see, so far we've considered a situation of a closed universe, right, where we had ADS and there was nothing around. And then, however, you can also consider the following setup where you have ADS, you have a black hole, and then you have a bath around it.
So, Brad, there's a question in the chat.
Huh.
Since the boundary Hamiltonian is defining the time evolution, can we say it keeps the information that we can recover using the correlators you're talking about?
Yeah, you could think of it that way. The boundary, you use the boundary Hamiltonian to kind of, go back in the past and see what came from there. If you actually try to do it using time evolution, you might run into many different issues. But using, that's why the protocol I presented never tried to do time evolution, but instead use this projector in the vacuum. I think it's a clearer argument that way. But indeed, one more argument you can think of is that because you have access to the boundary Hamiltonian, you can kind of, evolve to the past and see where the black hole came from, and then you can see what the infalling matter was.
I think so.
Okay. So you see, sorry, is there another question? I can't hear anything. Is there another question?
No, there is no other question. I think he's saying thank you.
Okay, thanks. Okay. So, you can also think of this kind of a setup where you have ADS and you have a bath. Okay. In this setup, what we've been saying, doesn't work because, the Hamiltonian is no longer a term on the boundary of ADS. Right? So now the Hamiltonian, because this bath is non-gravitational. And this is the setup in which islands emerge, and islands emerge as some region inside, which is discussed by part of the bath, right? So you have an island here. So there's no contradiction between what I said and this picture of islands. It's just that the setups are different. This is a setup where you've taken gravity and you've switched it off, and now you have a non-gravitational bath. And then some part of the bath, which is sometimes called the radiation region, like let me call this region R. This region R describes some part inside, which is the island. And there's no contradiction between what I said and what we're saying here, because in this setup now, gravity doesn't extend out. And in fact, the Hamiltonian is not a boundary term. The Hamiltonian is no longer a boundary term here. Rather, it's something that involves an integral from here to here. Okay. However, there's something, even then, this picture I presented is useful to understand this question that sometimes asked, even in islands, which is how did information enter the bath? So for instance, there was a paper by Martinek and others last year saying, well, the information was in the black hole. So you coupled it to a bath. So how did the information jump from the island to the bath? Okay. And well, the way you should think of it is precisely in the language that we've been describing so far. You should think of it this way. First, think of the ADS, black hole. This is ADS. Okay. And all information is present here. Then at the next step, you couple this to a bath. So now I'll add a bath. Let me. Now I added a bath. And well, information was already present here. So of course it flows into the bath. And once again, it's important, information doesn't jump. The information flows into the bath locally. Now, when it flows into the bath, of course, the information that was present here about all the black hole, it gets separated out in the bath. And indeed, what happens is, some part of the black hole now there's some island inside. And this island is described by what's in R, and the rest of the geometry is described by what was originally on the boundary of ADS. So these pictures are consistent with the fact that initially all the information was already available at infinity. And then you couple things to a bath, you had just local interactions. You don't have to do anything else. And so it's natural that the information flows in the bath, and then you can ask different parts of the bath have information about what, and that's where this island proposal comes from. But once again, the physical point I want to emphasize is in all of these stories, it is never that information is jumping. Rather, it is that the constraints, force information to be localized in a certain way. And, that's what also useful if one thinks in the paradigm of islands. Okay. Okay, so let me stop here. I see there's actually a question here. There's a small corrections argument by Samir Mathur. Okay, this is a good point to address that. The small corrections argument by Samir actually assumes assumes the following. It assumes that every bit that is emitted, is emitted in such a way it doesn't know about what went into the past and it doesn't know about the infalling matter. Right? And you see that, so that's some assumption of locality. It's some assumption that the information is inside the black hole. And well, if you try to change things in some way at the horizon, in some small way, you wouldn't be able to do it. And so, that's the reason that Samir likes fuzzballs, right? Because he wants to say, well, the information is really available at the horizon in the fuzzball, and therefore the information emerges the way it does normally. The difference in what I said is that that's not wrong in some very deep way. It is true that the Hawking radiation that's formed has information about the infalling matter. However, it's not happening by modifying the classical geometry by means of a fuzzball. Okay? So the objection that one has to a fuzzball is that you think of a fuzzball by saying, look, here's a classical solution, and that classical solution has some imprint of the information of the black hole. So there's no black hole really, but rather there's some ball of fuzz there, which really has information about what went inside. What I'm saying here is that, you don't need to do that. In gravity, it's already true that the information is available at the horizon. It comes from looking at the constraints. So you can have a classical black hole, and you can also have information available without modifying the classical intuition that you have, or without saying that, the black holes don't exist, but only fuzzballs exist. Okay. So the small corrections argument by Samir has this tacit assumption, which is that, what's emitted now doesn't depend on what was emitted in the past, what was emitted some other time. And so it's really an assumption of exact locality of some split property. And so that small corrections argument, I don't think is correct once one takes this into account. And in fact, that's the way the fuzzballs, go past that argument, right? The Hawking radiation is still thermal, but the fuzzballs go past it in this way. And I think that, we can discuss this more, but the difference in what I'm saying is that I agree that, of course, the Hawking radiation that comes out has to have information about the infalling matter, but it doesn't have to, that doesn't require you to give up the picture of a black hole as a classical geometry. The information can exist in some other aspects of the wave function, which don't have to do with the classical geometry. Okay, let me stop here, and if there are questions, I can take them.
Okay, before questions, let us all thank Suvrat for this excellent lecture. And I think there are some questions.
Yeah, okay.
So I can ask a question about the island scenario. So for all the proposals in the island, always come with the replica wormhole solution, existence of replica wormhole solutions, right?
Yeah, but that's a Euclidean picture.
All the concrete examples we have seen is where these islands are realized via this replica wormhole.
Yes. So,
but these are really Euclidean, or in some sense complex. You have to look at complex Einstein equations in some sense and look at these geometries, right?
Right.
So if we take that seriously, that we should look at all the complexified solutions of Einstein's equation, then would that also not affect the algebra of observable sets Cry? Should we then complexify Cry and?
So in the island, sorry, just to say once more, when you say replica wormholes, what you do is you really take a bath like this kind of geometry that I've drawn here, and then you make a cut here, and then you do the replica. This cut is made in a non-gravitational region. And then you look at how you can fill in the cut by gluing together many different replicas. So you're trying to compute the entropy of this part, right?
But this Maxwell scenario, I guess it's a scenario where it was really looking at this. They don't have a bath, right? They have asymptotically flat geometries, and they really had this picture where you have replica wormholes which connect one copy of asymptotically flat geometry to the other behind the horizon. Some wormhole emerges, baby universe emerges behind the horizon. And
yeah, okay. So we should understand that better. I know we've discussed this in the past. I don't have something very, very precise to say there, but it surely can't be that the asymptotic structure of the algebra is modified, right? It's presumably something else that's happening. Maybe you have more comments on this. In this case, in the case where you have ADS coupled to a bath, which is where I understand the island story well, I think there's no I think it's consistent. It's a picture where you have a by adding the bath, now the Gauss law no longer holds, and so the information has gone into the bath. And in the Euclidean perspective, you can compute the entanglement wedge of the radiation region by doing the replica wormhole trick.
Yes.
Okay, if you're really in flat space and you want to do this Morrison story, I don't understand very well. Maybe if you have comments, why don't you go ahead and make them?
No, we will chat later. It was just a question that should we I mean, if you take those solutions seriously, means we should look at the data at Scry, which is complex, not real. And I mean, it was just a question, really.
Okay. Sorry. Why should we do that? Like, why shouldn't we be in a Lorentzian theory where you have some metric and you have some real fluctuations? Like, why should we?
I thought this replica wormhole solution to the extent understand are not real, right? I mean, when you glue the replica wormhole in a Lorentzian asymptotic.
Yeah. But let's say here, all the discussion I was trying to present was purely Lorentzian.
No, I know. I
don't think why should we have to do this or
I mean, if we take that scenario seriously, that we need to look at complex solutions to somehow resolve the then that would mean from the perspective of Scry, we should look at different topologies of, I mean, I don't have anything precise. It was just,
Yeah, Suvrat, can you hear me now? Hello.
Yeah.
Sorry, to trading with my question, when we define this vacuum projector for the algebra, how do we choose the vacuum for a particular observer also or a region?
The vacuum is presumably unique, right? Or maybe it's in flat space, a 4-dimensional flat space might be degenerate, but in ADS, it is presumably a unique vacuum. So at least that's an assumption that I was making, that your theory has a vacuum which is unique in ADS.
Yeah.
On flat space, there's some vacuum structure, there's some vacuum manifold, but it's not observer dependent. It's a vacuum.
And
it's the state of lowest energy.
Yeah, for a given algebra, like these Witten and others have been writing these papers, they say that we choose a particular region, and like let's take a simple example of spin chain or so. Then you take a precise configuration in which this spin chain is in, and call it to be some vacuum state for all practical purposes, and then you operate the algebra on it to construct the
So that's this kind of a construction that I was discussing. Here, in this kind of a construction, you could take some state psi, and then you could construct a little Hilbert space, which was obtained by acting with this this co-strained algebra on psi. Right. So indeed, if you co-screen the algebra, then you could take some state psi and you could construct a little Hilbert space by acting with A on psi. And then within this little Hilbert space, you could ask questions about, what's the commutant and so on. If you want to ask questions about the full algebra, then, the vacuum is the vacuum.
Okay. Then you'll have to go to global vacuum, and you have, Okay, thanks.
Suvrat, so kind of trying to connect two things. When you talked about the atypical state and the construction of approximately local operators in the bulk, in the gravitational theory, does that say anything about the information loss problem?
I don't think so. I think that if you want to ask questions about information loss, then this is not the right, then you shouldn't be co-screening things. So, what this tells you is that why it is we see local things around us, right? We should be seeing local things around us. It should be pretty hard for someone at infinity to determine what's happening here. And this tells us why that's correct. But if you want to ask questions about, information loss, then you shouldn't be asking anything coarse-grained. Then you should be asking fine-grained questions. That was the point I wanted to make here. To ask about the purity of radiation, you should really ask fine-grained questions. Then you shouldn't ask coarse-grained questions.
Okay, so can I say that the absence of atypical states are important for
the absence of what states?
Atypical states.
Absence of atypical. No, sorry. Why absence? I was just saying to answer the question of information loss, you should take seriously the algebraic analysis we were doing yesterday, which tells us you don't have split states in gravity. So it tells you that, if you look at this Hawking argument that, the horizon is information free, that's not correct. Okay? So this is if you want to ask questions about information laws, then you can't also coarse grain and say, well, I want locality. If you want locality, you have to coarse grain, but then you shouldn't ask about information laws. If you want to ask about information laws, then you should fine grain. Then you can't say, well, I also want my intuition from quantum field theory to hold. I want information to be here and not be there, and so on. So you can't have both.
Yes. Actually, to not coarse grain, I was trying to connect it with the absence of atypical states, because
I don't think atypical states or typical states matters here. I think here the information laws, the question here is really whether you're coarse graining or not, and you shouldn't be coarse graining if you want to ask about information laws.
Okay.
Yeah. Hi.
Okay.
Trailing to the same logic. When we connected this bath for answering this information problem, then we still ignored the Gauss law, right? We permitted.
No, the Gauss law automatically breaks. When you connect the bath, then you see, because you added a non-gravitational thing, the information flows. So you don't need to connect the bath, by the way, to answer this question of information loss. That is, it's already clear that the information is available outside. What the bath lets you get is a page curve. So, the page curve in the end was derived on some basis of locality, right? It was derived, which is not correct in the gravitational theory. So if you add a non-gravitational bath, then you can make that intuition, which was not correct in the gravitational theory, you can make it precise. You can say, well, here's a non-gravitational bath, and in this, the Hilbert space factorizes, and I can compute the page curve of some region R with its complement. And the bath R kind of takes all the information which was present on the boundary and redistributes it within the bath. And then you can ask, how it's redistributed and how do you get a page curve? But
thanks. Yeah.
So you need it for the page curve, not to answer the question of information loss, but you need the page curve
One more question. When we connect this bath to, let's say, just to get the islands or get the information. What happens to the Hamiltonian constraint on the theory inside?
So the Hamiltonian. So this is the thing we were discussing yesterday. When you connect the bath, there are several issues. You might have thought that the Hamiltonian constraint, you have some normal theory of gravity here and you have something here, but in fact, the boundary conditions also back react on the geometry itself, and they give the graviton a mass. So the constraint that you have now gets modified, and that it looks like the constraints of massive gravity.
I see.
But this is some back reaction of the bath on the geometry.
I see. That could be understood. Yeah. Okay. Thank you.
Okay, Nirmali, I should also run, so I have to.
Okay, thanks, Suvrat, for this set of lectures. Let me just stop recording now.
Okay.
Sorry, just a small